Thank you, and thank you very much for the staff. My name is Luca, and you see here me wearing a different hat than usual. I usually will be coming here to you as a machine learning engineer. Actually, nowadays I'm here as an open source maintainer. Who's an open source maintainer here? Okay, I see quite a lot of people. Does anyone have ever actually heard about conformal prediction? Okay, quite a few people. That's cool, that's cool. That's a great energy. Let's just give like a round of applause to the organization. Okay, guys, let's just show a bit of energy. Come on, guys. Oh, okay. That's a lot of energy for London. It's my second time here. I'm so glad there is a great vibe. There is a great weather. No, actually, wasn't the one. But I mean, there's so many wonderful things about London. And I was talking with Marco from Polars about this yesterday. And what other greater thing isn't there in London, in the United Kingdom, in the whole of the United Kingdom, than this? Okay, really? Okay, really royal, really attentive, built-in floating system, real fluffy, right? Very bouncy. The Corgi is the majesty of the Britain, right? Who doesn't agree here? Of course, that's what's supposed to be, right? No one raises their hand because the Corgi are wonderful. But Corgis can be much more than that. They can be duplicitous. They can be tough to spot. And I see them anywhere on the road. But suppose you want to train a model to recognize a Corgi, right? What would you do if you see a Thorgi, right? Very brave. What would you do if you saw a Zorro Corgi, right? What would you do if you want to train a classifier? You clearly see the Corgi, right? Right? Okay. But it's hard. And when you train your models, you want your models to not only to output the true prediction, but maybe you want them to give you a sensation of what prediction are tougher to spit out compared to others. For example, on the left side, if you just have regular Corgis, it might be a prediction probability. It might look like this. On the other hand, a tougher prediction might look like that. And you would like your models to give you hints about how bigger or wider your uncertainty is about the model when you have to explain to them. And this trip is something that started, a while ago when I was when I wasn't still a maintainer about functime. Let me just turn on a timer. Because I was tasked with a really small feature. Actually, I was scouting through the good contributors, the first good contributor, like good for starters, series of issues. And I found one, we should make plotting, we should support plotting for some uncertainty quantification features that we have. And then I was looking into the code, and then I found out that functime implements an algorithm for returning conformal intervals, actually prediction intervals of your forecasting, which is called NP. And so today, in the next 30 minutes or so, I would like you to give a vibe of what options we do have to build uncertainty quantification in our models, and how we might want to get familiar and what it takes to be familiar with conformal prediction, which is the framework that the library that now I maintain uses. And basically explain what it takes to build a conformal prediction algorithm, and especially analyze the NP, which is a shortcut for ensemble batch prediction intervals, which is a conformal prediction algorithm for time series forecasting. We will do a brief intro for functime, and then, since we're really dangerous, we really feel dangerous today, even though it's last session, we would like to showcase them live in functime. Really scary. So that's the roadmap. Seems a bit too much, but I think we can manage. So let's get started. There are plenty of options for uncertainty quantification, and I'm glad I'm not seeing here people from PyMC. They were around yesterday, but I don't think this slide is full Bayesians, right? Any Bayesians here? That's okay. Phew. Wow, okay. I dodged the bullet. But basically, usually, what do we do when we try to see if our models are classifiers, but also, let's just talk about classifiers for a moment, right? When we want to see how well they behave, right? How sure they are about a certain prediction. Well, we usually just say, okay, we just call model dot predict proba. Although those don't really represent class probabilities, like real probability. They look like those, but they aren't, unless your model is calibrated. Now, calibration is one of those avenues that I've been exploring preparing this talk, and it's been really interesting, but I can summarize it in two ways. The first one, read the manual, because here you have two links for a couple of scikit-learn pages in the documentation that are really well done, and we'll tell you a bit more about what it is for a classifier to be calibrated. And then you also see this plot that comes from those pages. And it looks like a lot to digest, but it's really easy. If you think about it, on the diagonal, you will see what a perfectly calibrated model looks like. So basically a model, when it says that 0.6 is the class probability, then 0.60% of the time you will see on the data that label. But usually when we train models, and this is just taking a random data, so it's not like this for every model on every data set, right? But when you train some models actually tend to behave like more consistently, be more calibrated. Like the biggest example of which is the unregularized logistic regression. If you regularize too much, then logistic regression will yield uncalibrated predict probabilities. But some other algorithms, for example, the support vector machine, might behave differently. And you see how to read this plot is when the machine, like when the SVM classifier tells you that the predict probability is 0.4, in the data, you will actually see that the frequency of the class whose predict label was 0.4 is actually closer to 0.2%. So actually half the kind of, so you say, probability or confidence that the algorithm had. And the same goes on the other side. When you see that the model spits out a 0.6 label, then you will notice that actually the frequency that you find in the data is closer to almost beyond actually 80%. So this is why you need to calibrate your models, but most importantly, why maybe you shouldn't trust those, and you might want to find a more robust alternative to estimate your uncertainty about your point predictions. Another way to generate these kind of prediction intervals is for your Bayesian friends who use posterior predictive intervals, which are an amazing tool and will work if you're a Bayesian, but that's a catch. Those intervals are based on distributional assumptions about the data and the distribution family that you chose. And I'm no Bayesian, so don't quote me on this, but the gist behind Bayesian regression, Bayesian modeling is that you need to assign like distribution to the data and model your data and the parameters of your model using distributions. So if you're wrong, then your posterior predictive intervals are wrong. And you might be wrong because, well, you're just wrong and you guessed the wrong thing. But even when you're, like, even if you're sure, like really confident about those distribution, the data may just prove you wrong, right? So talk to your domain knowledge experts about this. But in general, when you cannot reliably build, you might end up in a situation where you cannot use a Bayesian model. A, for example, like I am, I'm not like a Bayesian, so I wouldn't know how to train one of those models. Or B, you're working with a fitted estimator, something that was already in production. So what would you go like to your manager and say, yes, I think we should just throw away the stuff that's been put into production for 6 months or so. I mean, this happens all the time. So, but just imagine like coming up to a manager that tells you, I would like to have like a more robust estimate of the error of the prediction that you give and with the uncertainty. And you're like, I think we can just redo the model from scratch using a completely different framework of modeling. There has to be a better way, right? And finally, some people say, well, let's just bootstrap it. And I'm not an expert on this field, but I saw a couple of papers saying that bootstrapping actually underestimates the true variance. And I see somebody nodding here, so I might not be totally wrong on this one, I'll be totally far away from this. So the point is, popular alternatives to estimate the uncertainty or provide like an attempt to quantify the uncertainty about your prediction may have their downfalls. They're valid tools, but you need to know how to use them, okay? And so here I come with another tool to add to your belt, and I do not claim that this works. A, because I'm basically new to it, and B, because I don't think there are, and it's good to have such tools at your disposal. And this tool is conformal prediction. Conformal prediction makes a bold claim. It's a straightforward way to generate prediction sets for any model. Even Bayesian models. You could technically use conformal prediction to generate intervals for Bayesian models. Not an expert on that, but the literature says so. And they make the bold claim that if you have a fitted estimator, you can take a bunch of data and use it to calibrate the model and provide and make it capable of outputting prediction sets, right? Prediction intervals. And in doing so, they do not require any sort of distributional assumption. And they also, by statistical proof, right, they guarantee you that the prediction set has a 90%, for example, if you set the uncertainty level to 10%, then 90% of the time, the prediction that you will be in the interval that you generate. So it will be calibrated, to put it in a mild way. And it does so by making no distributional assumption about the data, a small caveat. But most of the time, it requires another assumption that is called data exchangeability. And I say most of the time because conformal prediction isn't just one algorithm. There are plenty of them. And they mostly follow the same recipe. And some of the steps say, okay, we make no distributional assumption about the data except data exchangeability. Set aside some split of the data called calibration dataset that you will use to generate a sort of measurement that you will then use to generate prediction sets. All on the same page about this so far? I think so. I still have all people nodding. Here the tough part comes. Data exchangeability, it's an interesting take, and I've been thinking about it, and I do not completely agree with the claim that I hate pointers, but I mean, I completely agree with the claim that these are handy to use, but still, you see here that some people say, okay, that it doesn't make any distributional assumption about the data except data exchangeability, which is a milder version of IID. Basically, you take away one of the I's. Wikipedia says that an exchangeable sequence of random variable, an exchangeable sequence is a sequence whose joint probability distribution does not change when you swap the elements around. And if you go on cross-validated, which is the Stack Overflow subthread for statistics, you will find this elegant answer that says basically exchangeability is a way to talk about symmetry in the data. In the sense that your data is symmetric because you can swap the elements and it will retain the same distribution in terms of, I mean, it requires the same, that the data comes from the same distribution where the ID comes from, but it doesn't require independence. And this is a powerful concept. And I really struggle to see how this is not a distributional assumption about the data. But in a way, the only requirement, the big requirement for most conformal prediction algorithms is, well, the data all needs to come from the same distribution. And here, the people that have worked with this already might see where I'm going with this. But keep in mind, exchangeability. So in a way, all the data needs to come from the same distribution. That's okay. Now, let's talk about tough stuff, okay? Talking about coverage, because that's the thing that the algorithm gives you, right? That's the thing that mathematically is proven. If you have a level alpha of uncertainty, then your conformal prediction algorithm will return a prediction interval, and you will have the statistical guarantee that 1 minus alpha, so if alpha is 10%, then it will be 90% of the time, the prediction that you make will be in that interval. And if you look at the maths behind it, that's a bit of a scary formula, but we will have to see a couple of those, so you better get familiar with this. The alpha is a user-defined confidence threshold. Cool. The P, actually Y test, is our prediction, and C of X test basically is the function that returns the prediction set. And then this 1 over n plus 1 It's just an adjustment factor. We can pretend it's not there because as the calibration set grows bigger, you usually don't use more than 500 or 1,000 points for that in the literature. So it's still going to be negligible. But still, if you read this, it makes sense. It basically just says in maths what I've been telling you so far, which is, well, what you are guaranteed to have after you use the conformal prediction algorithm is a prediction set, C of X, that depends, basically that uses the labels, the data that you use to make the prediction, and you have the guarantee that the probability of the prediction that you make, Y test, is between 1 minus alpha and the alpha and 1 minus alpha. Actually, I'm a bit buzzed here. Yes, but this is actually, yes, this is the theoretical guarantee. The marginal, it's called, marginal coverage. Maybe tough to digest, but basically this says that on average, the prediction that you make will all fall inside an interval. And you have the statistical guarantee about that. I've been saying this a lot, because what comes after is a bit tougher. And it is the conditional coverage, which is another property that might be desirable, but it's not something that is entailed automatically by conformal predictions. And this property is a bit tougher to figure out. It looks like kind of the same, but it has a weird element, which is here. And basically says that this is not always satisfied, but it would be wonderful to have. And this property says that basically the prediction belongs to the conformal set conditioning on X. So basically what this is saying is that you are locally, you want that marginal probability basically to work locally. Let's just do a step back. When we generate Y test, we use X test and we build a conformal set out of that. But we also would like to have a situation where the probability of this prediction being in the interval is not on average, but is precisely local to that point that we're, basically to that vector that we're using to train the model on. And this is something that isn't granted, but it's something that can be pretty much well explained like in a more direct manner if you make an example. Suppose you're a doctor and you report prediction intervals for one patient's blood pressure, okay? If you use conformal prediction to build those intervals, then you have the guarantee that on average, all of those predictions will fall in that 90% interval across all patients. That's marginal coverage. If you want the conditional coverage to hold, you would like for that prediction that you make to hold for that specific patient. All clear? A bit less heads nodding, but still some heads, so I'll go on. So the idea is that, in a way, the theoretical guarantees like conformal prediction are powerful because they give you something that on average is, say, 90% of the time inside an interval, prediction interval. Cool. But if you need to be sure about the prediction that you make for a certain specific candidate, some or maybe most, I mean, you need to look for a conformal prediction algorithm implementation that holds for that conditional coverage property. In a way, you might be, if you just use an algorithm that just gives you marginal coverage, then you're not sure that for that specific observation, somebody might be, the prediction for that given point will be inside that average, that conditional, the conditional interval, that interval. And this is all the theory. Now, let's go on the practical side, right? I mean, I saw like many flavors, there are many properties. Okay, that's a bit more like in the clouds. Let's just go down to earth. The recipe between to make a conformal prediction algorithm is to update your subtitles to the slides. And it's really easy. You put on your hat, you take on like your pencils, maybe your erasers, and you just go there and you take your model and you identify a heuristic notion of uncertainty. Maybe heuristic is a fancy word for saying if you do classification, just take the predict probas. If you do regression, take residuals. That's it. That's a heuristic notion. Heuristic in a sense that it doesn't need to have theoretical guarantees, right? It doesn't need to be outputting proper probabilities, right? And then, and that's the most important part, you need to define a ranking function that sorts all of those heuristic measurements that you got from the first step, from the largest to the smallest, where larger value means that your prediction has the biggest degree of uncertainty, the biggest disagreement between X and Y. And then what do? You compute the scores on all the calibration data, the data that you set aside, and then what you do? Well, you just compute a quantile. So out of you use all the calibration data to build basically a sequence of confidence scores, of non-conformity scores, they're called. And they will differ in value, but they will basically just be an unsorted version of a way that measures, of a function that just sorts the function sorts the prediction from the most uncertain to the least uncertain. And then you use basic maths, right? You quantile Q. That quantile Q, remember, is the 1 minus alpha quantile plus the adjustment factor, so whatever, but pretend it doesn't exist for a moment. And so, for example, you compute the quantile of 90% quantile, right? The ninth quantile. And you use that value to build a prediction set. And that prediction set is the set for which basically you just collect at prediction time. Basically, step back. When you just use the calibration data to take out that Q, that quantile Q hat, to be precise. And at prediction time, what you do is just simply take the model, build the prediction, and then go back, look at the predict probabilities, and then take all the predict probabilities, for example, that are below the Q value. So basically you compute the non-conformity score using the predict probabilities, and you take in all of the classes or all the labels whose predict probability score is below the quantile that you found. Looks simple enough, right? Okay, this is scary. Nobody was nodding here. I should have a slide for this, but actually, I think the best source of this is just the papers. So we can go here and look at the figure. So what you do, look. And if you see the math here and the code here, this might be a bit more familiar. So what you do here is you compute the predict probabilities of all your classes. The calibration scores here, use just a really simple algorithm. You just take the biggest value, you just do 1 minus the calibration score. And you compute the quantile, and the quantile is just the basically 1 minus alpha of that array of calibration scores. And that's where you use the holdout data, the calibration data, and that's basically 1.1 and 0.2. Point 1 is you compute the calibration scores on all the data, then you sort it and take the quantile. Then, when you do prediction here, for example, when you use when you do prediction on the next value, so when we have unseen data and you want to make prediction whether your corgi is a corgi or a thorgi or a ghost thorgi, whatever, you just take all the class labels whose predict probability is above or below, actually in this case is below or above minus the quantile. So basically, suppose here I have cat, thorgi, insect, bat, and corgi, then my prediction set will just contain the labels whose predict probability is higher than the quantile that we found. Better now, right? Yes, okay, there we are on better part. What we saw here is just an implementation, one of the possible implementation of a conformal prediction algorithm that is called the split conformal. Wow, okay, I need to run. I thought I had more time. I thought there were 40 minutes, but that's better. So, and this is just something that you can take home with. And this is okay, right? So the recipe is simple. We take the data, we use this heuristic notion, we take class probabilities, we compute the non-conformity score, These scores basically rank the function from the least certain to the most certain. Then we compute the Q value, and then we basically make new prediction, select all the labels, or subtract or add in case of regression, that fall below the quantile. Cool. But remember, I told you something. We need our data to be exchangeable. And also, I need to report to those people that were here to watch a tutorial that was scaling uncertainty prediction for time series, right? And remember what I was telling you before about data assumption and exchangeability. All the data needs to come from the very same distribution. What happens if your data has a drift? What happens if your data is time series data? Well, it's not exchangeable. So how do we do conformal prediction? Why did I have to sit you through 22 minutes of this for nothing, right? Well, it turns out clever people found a way to use conformal prediction for time series forecasting. And this is really clever. The paper was published on the proceedings of the Conference on Machine Learning Representation. And this monstrosity is what they came out with, okay? It's a conformal prediction algorithm that has a lower bound for the marginal coverage and conditional coverage, which means that if you use NP to fit a model, a machine learning model, then you will also have a theoretical guarantees that the prediction that you make will be in that 90% interval or 1 minus alpha interval for that point, which is incredibly powerful. What you need to pay for this is understanding this bit. But basically, and I do not have this annotated, but this f of 1, and actually this f of t to the minus 1, basically the inverse of this function is just simply, this is a cumulative function, a distribution function, but you don't need to be extremely scared about this, but what basically this is just telling you is that your prediction set is f of x, basically the prediction that you make, plus a delta, and the prediction minus a delta, because f plus f of 1 minus alpha plus b star is just, if you just is this minus the other thing, right? And there are plenty of things to say about this, but the most important is that basically this says, okay, your prediction will be the point estimate plus an interval around it. An interval that might not be symmetric. So it might be smaller on one side and bigger on the other. So you can tell whether your model is under or over forecasting on average more for that predict precision. And basically you see here that 1 minus alpha is something we saw. The fancy boundary thing that we're telling about, the explicit lower boundary that they prove mathematically is there, is b star, beta star. And this beta star is the beta star that satisfies a minimization problem that is basically the one that makes the difference, basically the boundary smallest. That's all, okay? Sounds reasonable, right? Sounds you got it, right? It was easier than compared to class probabilities. So basically just tell you, well, the prediction set is a prediction set where the lower boundary and the upper boundary are determined by an estimator of beta, where beta is the special beta that denotes the lower boundary. Basically, it tells you that your prediction interval will be a bit larger than it would be usually, but it will also have conditional coverage. So in exchange for conditional coverage, you have a bit of a smaller interval, a bit of a larger interval, sorry, and you find this beta parameter that gives you this boundary by just solving a smaller minimization problem that makes this interval the smallest. That's all. You need to have two assumptions for this. And we know that one cannot be data exchangeability because we are working with time series data. And in fact, they just make a different assumption. Two that, in their opinion, are milder. The first one is that when you're making a prediction, like for forecasting, you're trying to predict point t plus 1 given a series. And well, they just say, well, okay, the assumption that we make is that the point from point 1, from point t plus 1, the residuals of those time series are just IID. Cool, that's a property we want, right? Because we are always inspecting the residuals of a time series forecasting algorithm, and we want to see those that are flat, right? Because we want to see that we want to have extracted all the possible signals from that time series data point. And then the second the assumption, which I simplify a bit, is just that the model has a low error. So basically, that for the series, the sequence of error from the model, averaged is just basically not increasing or converging to zero. And they also provide a computationally efficient algorithm to do this, which is a bit different than the one that we're using and just requires to bootstrap your time series data. So you don't need to set aside some more data for the calibration data set. You just use the data that you already have, you do some bootstrapping in a fancy way. I mean, it's a recommended way that basically just takes the blocks, and then you specify a number of B of bootstraps that you want to make. You fit a model on each of those bootstraps, and that's it. You never fit a model anymore. You just basically make, okay, now I have 5 models or something that are fit on 5 different bootstrap datasets from the original data that I have. The prediction in sample for point I is the average of the prediction, and I use this to estimate and approximate an aggregated error of every prediction for every point that I have in my data set. And that's phase 1. And in phase 2, we just we take the new data that we need to predict, we take the ensemble of models that we trained, and basically the prediction of point t plus 1 will be the average of the predictors, the average of the prediction that every predictor made for that point. And then we finally take beta, and we find beta star for that point, which is the special quantile level that satisfies the equation that I gave you before. And then basically now we have a quantile, we have a point estimate, and we also have a prediction interval. Ta-da! Plus, another fancy thing is that when you surpass a certain forecasting window period, for example, suppose you're doing forecasting 7 days ahead, you do one of those estimates like, okay, t plus 1 is the average of the ones, t plus 2 is the average, blah, 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 and when you come to t plus 7, you just slide the error set that you made during the training set, and you add the new errors that you got while measuring when new data was coming in. And you do this, and it's extremely efficient, and I would love to show it to you with functime, but the point is that, just to make this short, and that's the scalability part, is that functime works at a reasonable scale because we use polars to massively handle parallel data like multivariate time series data, and we also use global forecasting, which is just a fancy way to say we train one model on every point in time. And we are able to provide you with all of those point estimates all at once, okay, because we implement, or we try to implement an algorithm, and this is some of the fanciness that functime will give you, but I can talk to you about later. And functime basically implements this algorithm, or tries to, because I'm not sure of this implementation. And that's basically the whole story about this, right? When I was coming, I was just hoping to build a plotting function that would basically take this, pivot this, which if you see the error message below here, I cannot still do. I'm really bad at pivoting since I didn't do a lot of Excel in my life. Yay, I see this as an absolute win, okay? But basically when I went through the code with this, I was like, I can A, optimize the polars code for this, and B, look at the paper about this very cool algorithm that gives you prediction intervals that are both working locally and globally, like on average and for that precise point, and find a new tool under my belt. And I see this really as a win because like being an open source maintainer forced me to set aside my work as a machine learning engineer and look into papers, into a new framework and fix this. And basically that's the whole story. I wish I could tell you a bit more, but I think we can talk about that later with question time. And that being said, here are a bunch of references, but I will share with any of you these slides. I usually upload them on GitHub. So if you need to share any kind of feedback about this presentation, because this is the first time I'm giving this talk, please do reach out to me. I would love to hear any kind of feedback you have, especially about functime, as well as taking any question. So thank you very much for your time. I hope I can entertain you with a new idea and inspire you to try out new things. Functime is a cool project that is built on top of polars, and it doesn't need to be the best time series forecasting library. There are many out there, but it is mostly like a fun exercise to tell you that polars can be used to build a lot of amazing stuff. And time series forecasting on multivariate data is just an amazing field where you can get a lot of absolutely massive speed gains just from using that. So I encourage you to check that out and give it your feedback about it. Thank you very much once again. Maybe you can come.
Okay. Good stuff. So we have 5 minutes for questions now. Can you raise your hand and I'll bring the microphone to you?
That's the scary part of the presentation.
That was a really great talk, thank you. These bounds that have to increase the variance of the individual person, does it just explode to it including every possible value? Is it still like a useful bound, or is it just such a large variance that it seems almost silly?
So, I haven't tested it empirically, but if you look through the paper, it's 50 pages-ish, but like the real thing is like 20 of them. But if you look at it, the training boundary is, given some boundary, it looks a bit like this. So it's a square of a logarithm function. So I think it shouldn't explode too much. But another alternative is, if you're just satisfied with a marginal coverage, then you can just use another conformal prediction algorithm, which will have like a smaller bound, but won't give you the certainty that the prediction for that point falls inside the point, the prediction interval. Thank you.
Thank you. Really cool talk, and I was not aware of this method of calibration.
Thank you.
It's extremely insightful. And my question is about the data exchangeability assumption. Is it true then that it's essentially like a common support assumption where we don't care about the distribution of this data at all, as long as we can slice this data, and then the first slice and the second slice have basically have the same sort of coverage, in a sense that they have the same distributions. And the second question is in that case, do we make any assumptions about the sample size, or are there any restrictions on the minimum sample size for this calibration to work?
Okay, so if I got your first question, basically the exchangeability assumption is needed because you could theoretically build the calibration dataset from any combination of points from the source. So you need the data to come from the same distribution, but it doesn't need to be independent, which is a fairly strong assumption that mostly always holds for cross-sectional data. But when you start to have data that has a drift, say COVID, just because the data before, after, whatever, new people, for whatever reason. So, but it can be weakened, or the algorithms can be implemented in a different way to work for time series data as well, or for data that exhibits a drift somehow. So I think that was the first question. Okay. Then the second question was the sample size of this calibration dataset. I don't remember whether there is a theoretical minimum size. What I think I read somewhere between 20 and 50, but that sounds a bit too small. I should double check that. But empirically, what I read in the first paper that I showed you, which is the first on the reference page, is that mostly 500 to 1,000 observation would do the job.
I think that would be the weakness of this method. I think the sample size would be the weakness of this method compared to, for instance, Bayesian correction, where we make some assumptions about the distribution and we can map certain data points to this distribution. Because here we have this data exchangeability assumption, right? So the sample size needs to be much larger, I imagine, compared to other calibration methods.
I cannot tell you yes or no. I think you're right. And if you're working with 50 data points or something, then of course you'd be better. I don't know, of course, but it might make sense to consider some alternatives as well.
Thank you.
You're welcome. Ooh.
Hi, thank you very much for the talk. I was just interested in one of the slides. You had the quote about from the Institute of Forecasting.
Yes.
Saying to move to efficiency rather than the process itself. Can you just maybe talk a bit more about that? That sounds quite...
Definitely. Thank you very much for the question. So, this is the idea that powers functime. This guy, who's not really a nobody at all, is on the board of directors of International Institute of Forecasting, which is basically one of the institutions that we look at in the academia full-time series. And he said, he's been working on SAP for a long time. He's been a manager of SAP for a while. And he says, forecasting on itself is inefficient. We spend a lot of time trying to build more accurate forecasts. But that's not the point, because they are a waste of management's time, even management's time, because people need to sit down and watch those forecasts and say, okay, well, are they really improving? Do we need to check that they're really improving? So what he advocates for is a different take on forecasting, where efficiency, where the effectiveness of forecasting is not just the accuracy that you get from the model, but is more of the how easily you can throw them out. Let's put it this way. So it is more of the, we should just move our attention from esoteric forecasting model, advanced, like really complex and cumbersome neural network that takes into blah, 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 from just the forecasting process itself. And have tools that give you an exceptionally fast way to extract and produce prediction that might not be the optimal ones, but they're easy to get out. And that's the philosophy that we built functime upon, to be able to scale forecasting effortlessly, because we use polar, so you could theoretically forecast 1,000 time series locally on your machine. I haven't tried like the upper boundary, but I have a 36 gigabyte of RAM of my MacBook, but still, you can take, I don't know, a really big VM from EC2, it could be like almost 700 gigabytes of RAM, and just, it will cost you like $3 or something, and you can train basically a gradient boosted models with clever feature engineering. It doesn't require that much feature engineering, but still you might want to add some rolling features, and then spit out some predictions. And you don't really need to, and we do one side of the efficiency this way, because you're able to iterate very quickly on multiple time series at once, spitting out a reasonably cool forecasting, because we use global forecasting, which the theory, like academia, as well as forecasting competition, show that you can fit one model on like multiple time series and it will yield acceptable precision and sometimes even state-of-the-art predictions for your data. And then the other side is the management process. But still we do the first part, which is efficient forecasting at scale, where the efficiency does not come from the incredibly powerful algorithm that we use, but it's the workflow itself. From feature extraction to diagnostics, going through cross-validation, because we use Polar, which is blazingly fast. We implemented the whole of TS-Fresh in functime, giving, of course, due credit, right? But it's running on Polar. So you can work on 50, 60, 70, 1,000 time series at once. Whereas usually you would have done just 4 loops maybe, and you will be still watching and the residuals of every one of them. Hope I answered your question.
Okay, thank you for the talk. It was really good. I was wondering if you could tell a little bit more about how is this bootstrapping strategy for time series?
So I think it's fairly easy, and in the paper they just tell you that it's, oops, wrong slide, maybe here. It's called block bootstrapping with non-overlapping blocks. So basically I think that just you need to define B blocks, or L, the length that you want your bootstrap samples to be. Say I have a time series of length 1,000, for example. I make 5 blocks out of those, and I divide my time series in 5 pieces. And then I take a sample of T points, so if I have 1,000 points for each of those bootstraps separately, and I make a new data set out of that. But I'm not extremely sure about the non-overlapping blocks, because if you look at the paper, they will tell you, and if I go block here, I was looking at this before this, they say split the training samples into L non-overlapping blocks. So they might even be overlapping up to a certain extent. I should ask the author, but technically you might have like a small overlapping of those. But basically the point is you have 1,000 points, you make 5 separations, 5 splits, so you have 5 splits of 200 points, and then you take 1,000 samples randomly with replacement from every one of those, and then you have 5 data sets. And then you fit one estimator on any of those, and then the estimate that you make are the aggregations, the average basically that you do on all of those. Not to test, but basically use those 5 blocks to compute prediction, and you ensemble those predictions. Basically you average them or take the median. As per the paper. Then you could do cross-validation, of course, and nobody prevents you from doing that. But it's not necessary to give you the prediction intervals. Thank you, welcome.
Okay, let's give another round of applause for.
Thank you. Thank you.